Hi everyone. So for this lecture, before we move on to respiration, because that's where we're headed next, I think it's probably worth our while to kind of try to continue where we left off last time. We were starting to integrate some hormones, and then we were starting to integrate those hormones within a bigger system. And now I think let's kind of take it to the next level of integration. It's probably worthwhile going through this exercise so you can start to see like where we're at and where everything is fitting in. So let's go through an example, like an example that we've seen before, and then try to kind of tie in a lot of the different things that we've seen. So let's mess with ventricular function. So let's go back to our an example of heart failure. So let's go left heart failure. So we're going to have a decrease in left ventricular function. So we've done this example a couple of times in kind of many different contexts, and so let's kind of continue with that. So if we go to our normal little schematic of the respiratory system, pulmonary, the systemic, capillary beds, the left heart, and the right heart, and the vasculature that connects them, pulmonary veins, systemic veins, pulmonary arteries. Okay, so we kind of know where we're at, little model of the cardiovascular system. And essentially what we have here is our decrease in left ventricular function. So if we're going to try to figure out how that affects the rest of the system, okay, we're going to have a decrease in cardiac output. So the challenge is here, right, which means I've got a decrease in cardiac output of the left heart. Because of that decrease in cardiac output, I'm going to have a decrease in volume and a decrease in pressure in the systemic arteries because I'm putting less volume into there, and I'm taking less volume from the pulmonary veins. So here we're going to experience an increase in volume and an increase in pressure. Okay, so now if we think about moving around the vascular system this way to try to figure out what's happening in our systemic veins, because I have flow from systemic arteries to the systemic veins, I have a decrease in P1 minus P2 over R, so therefore I'm going to get a decrease in flow into the veins. So I'm going to experience a decrease in volume and a decrease in pressure here, which is really a decrease in mean circulatory filling pressure, right? And then we know how is that going to affect venous return. We know that venous return is equal to mean circulatory filling pressure minus right atrial pressure over resistance in the veins. We're going to drop in mean circulatory filling pressure, so we're going to get a decrease in venous return. Okay, so that means we're going to have a decrease in cardiac output of the right heart, which means up in this region, the pulmonary arteries, we're going to have a decrease in volume and a decrease in pressure because of that. So now if we were to track back this way to find out how the change in the pulmonary venous compartment is affecting the pulmonary artery compartment, we would think of our flow equation, P1 minus P2 over R, and in terms of flow in this direction, we have just increased P2, which means we have a decrease in our gradient for flow from here to here. So if I have a decrease in flow from here to here, I must have an increase in volume and an increase in pressure. So, as we've done before, we do get, the further we get away from a challenge, the more difficult it might be to predict what's going on at a certain area. And so now we know enough, so this is how the body would get itself messed up. So now we know enough about how the body would now try to start to fix itself, right? Essentially, we've just indicated there would be a decrease in mean arterial pressure, and we know that that's a regulated variable. So how might the body respond to that? We have those high pressure baroreceptors. We have low pressure baroreceptors right over here in the right atria, sensing venous return. So pressure on this side are low pressure baroreceptors over here. We have stretch receptors in the right atria releasing atrionatriuretic peptides. So now, we kind of know more about, or can try to predict now, about how, not only how is the body going to get itself messed up, but how is the body going to then regulate to try to fix this problem. It's never going to be able to fix the problem because the problem is with the left heart, but obviously that's creating other problems that the body will then just try to fix because that's how it's wired. So when I look at one of these problems, I first like to think about sensors. What sensors do we have, and have we changed those sensors in any way? So the first obvious sensor that we have would be in response to measuring this mean arterial pressure. So remember, we have those high pressure baroreceptors, all right, sensing that mean arterial pressure, and with a drop in mean arterial pressure, it'll result in an increase in the sympathetic nervous system output and a decrease in the parasympathetic nervous system output. Okay, so from here, now that I've got my sensor and what my response is, I like to think about time. And so by time, I mean, what would the body be doing first? And so in terms of milliseconds to seconds. So I would think about everything that I'm directly connected to with the sympathetic nervous system and the parasympathetic nervous system. So for example, we know we are directly connected to the heart through the parasympathetic and the sympathetic nervous system, right? And so let's think about the heart. So in the heart, we are directly connected to nodal cells. Right, and what did an increase in sympathetic nervous system activity do to nodal cells? It caused an increase in heart rate. And this would cause an increase in cardiac output, which would then cause an increase in mean arterial pressure. So the body is wired this way because it wants to fix its problem. We know from that increase in heart rate, we would have an increase in contractility. Which would result in an increase in stroke volume, an increase in cardiac output, and an increase in mean arterial pressure. Okay, we're working, the body is wired to fix this problem. So where else in the heart are we connected to? We have direct SNS innervation into ventricular myocytes. Right, where we are going to increase contractility, right, which is going to increase stroke volume, increase cardiac output, increase mean arterial pressure. Okay, perfect. So where else are we connected with, directly connected to the sympathetic nervous system? So we know we are connected to vascular smooth muscle, and vascular smooth muscle cells of the arterioles. Okay, so here an increase in SNS stimulation to arterioles will cause an increase in vasoconstriction. An increase in vasoconstriction of most of the vascular beds in the body is going to cause an increase in total peripheral resistance, which is going to cause an increase in mean arterial pressure. All right. We have direct SNS innervation into veins. Here we caused venoconstriction. Change that pressure volume relationship. This would increase, here that venoconstriction would make the walls a little more rigid, causing an increase in mean circulatory filling pressure. This would cause an increase in venous return, which would cause an increase in cardiac output of the right heart. And then if we do the work, as we've done already, we will see that will increase cardiac output of the left heart. So let's say we increase cardiac output of the right heart, which will then, if you do the work here, you'll see that will increase cardiac output of the left heart, which will increase mean arterial pressure. All right. So again, the body is working towards fixing the problem. Okay? So then after we kind of get our immediate responses out of the way, I think where else are we connected? Can we tap into potentially tap into hormonal responses? So this is starting to tap a little bit into not the milliseconds to seconds time scale, but the seconds to minutes time scale. So we know we are directly innervated into the adrenal glands. Okay, where we're going to get an increase in epi and norepi release. Right, and that is pretty much going to support all of the above, right? Because all of the above was based on an adrenergic membrane receptor population, and so now we've got a hormone out there, so it really just supports all of the above. Okay. And we did see that epi was a vasoconstrictor of afferents greater than efferents. Okay, so this is going to work to decrease GFR. Now, the reason we would be decreasing GFR, we want to decrease the filtration rate, right? Because we want to essentially decrease the amount of filtration that's happening at the level of the kidney, trying to keep all the volume we have in the body. Because if we can increase volume, we can increase pressure. Okay, so again, this drop in GFR is working towards the same increase in mean arterial pressure goal, except here the vehicle it's working through is a change in volume. Now, the last lecture, we did talk about direct SNS innervation into the arterioles of the kidney, the afferent arterioles. So let's think a little bit about the kidney. We did talk about SNS innervation and the release of renin from those renin-secreting cells. So we're going to increase SNS, so we're going to increase renin. Right, so once we increase renin, we're going to increase angiotensin II. Right, so now because it's the brain, the coordinating center, the sympathetic nervous system now calling for renin, we're going to get larger amounts of renin, and then systemic angiotensin II, so not just that local stuff, but now larger concentrations systemically. So we're going to have a vasoconstrictor of afferents equal to efferents. Right, so this is an attempt to decrease renal blood flow. So let's stop flow going into the kidney altogether. That'll help us not lose volume down there. Increasing angiotensin II, it was a systemic vasoconstrictor. Right, it's a systemic vasoconstrictor. So if I start to vasoconstrict systemically, I'm going to increase total peripheral resistance. I don't know what that is. Total peripheral resistance, right? And this will increase mean arterial pressure. All right, we're starting to get our hormonal constrictors out there. We know that angiotensin II will stimulate the production of aldosterone. So we're going to increase aldosterone production, which is going to increase sodium reabsorption. So at that thick ascending limb, and if I'm increasing sodium reabsorption, this is going to increase water reabsorption. And the hope here is that that is going to increase blood volume, which is going to increase mean arterial pressure. All working towards the same goal. Increase angiotensin II, I'm going to increase ADH. Remember, they all come out as a package. Increase ADH ADH does many things. First of all, it's a vasoconstrictor. All right, so if I have systemic vasoconstrictor, I'm going to increase TPR and increase my mean arterial pressure. Right? What else am I going to do? I'm going to, with ADH, we're going to make it more permeable down at the kidney. Distal tubule in the collecting duct, so I'm going to increase water reabsorption in an attempt to increase blood volume and therefore increase mean arterial pressure. And ADH at the level of the kidney, right, as part of what it was doing at the level of the kidney. It was a vasoconstrictor of afferents greater than efferents, right? So now I'm going to decrease my GFR. Again, an attempt to decrease the filtration down there to keep volume in the body and not potentially lose it. Excuse me. All right, so now where are we at? Where else can we go? We had changes in, I guess, the high pressure baroreceptors, stimulation of the hypothalamus, right? We need to think a little bit about that. So rather than that direct SNS connection out, we did have the relationship with mean arterial pressure and a plasma ADH, right, through the hypothalamic release. And that graph looked something like this. And we dropped our mean arterial pressure, so through that pathway, we should fully expect to see an increase in ADH, right? And that's really just going to do the same as above. Okay, so that's working to support above. Okay, so I think that that's pretty good for high pressure baroreceptors now. So we've gone milliseconds to seconds, right? We've gone milliseconds to seconds. we've gone seconds to minutes, right, with our hormones, and then some of these hormones working at the level of the kidney, right, in terms of increasing reabsorption and that kind of stuff. That's kind of an hours to days type of thing. So the way I like to try to think about these things is I think of my sensor and then I work through the 3 different time scales. And when I think I'm done there, I'm going to pick another sensor and then work through the different time scales, right? So we had another sensor, let's go our low pressure baroreceptors. Okay, so we had those. Those were essentially with a decrease in mean arterial pressure, we're going to increase ADH, right? So that was through that hypothalamic connection. So really that just supports all the thinking that we've done already. So I've done that. Other sensors, that atrial stretch receptor, let's go there. Atrial stretch receptor. All right, so in the right atria, we had those cells that were releasing atrial natriuretic peptide, and since we had a decrease in mean circulatory filling pressure and a decrease in venous return, we're going to get less stretch, right? So if we could decrease stretch, is going to result in a decrease in atrial natriuretic peptide. So now we're inhibiting something that was going to be inhibiting ADH, renin, angiotensin II, and aldosterone. Right, so if we're inhibiting that, this will result in an increase in renin, and then we get the whole suite out, right? Increase in renin, increase in angiotensin II. That's going to result in an increase in ADH, because angiotensin II stimulates the production of ADH, and angiotensin II also stimulates the production of aldosterone. Okay, so good. So really once all those are out, it really just we kind of just repeat all the thinking that we've done above. So other sensors that we have, we talked a couple of days ago about high pressure baroreceptors right at the level of the kidney, right? Remember those guys? They were so high pressure baroreceptors at the kidney. And what we're going to get here is, remember that relationship? It was pressure in the afferent arterioles and renin release, and the relationship looked something like that. So we would decrease mean arterial pressure, so we would decrease pressure in the afferent arterioles, so we would increase renin, which is going to increase all the stuff we've already talked about. So we've already done our thinking on that. Okay, you can work through what's going to happen with fluid flux. Okay, so I'd encourage you to work through that to see what the body would be doing in order to in response to what we did or how we messed up the cardiovascular system. Okay, so can you start now to see this very lengthy answer here? Start now to see, well, I can't even get it all in one shot. You can start to see how everything is going to be coming together, okay? And how we started from learning about how the body was going to be messed up with a perturbation, And now that we've plugged in the sensors and we know what they're connected to, how the body will start to regulate to try to fix its problems. The problems it thinks it has are the things that it has sensors for. Okay, like mean arterial pressure and stretch at the heart and venous return, that type of stuff. Okay, so essentially attacking these kind of problems, we did first identify the receptor, and then with that receptor think about 3 different time scales. So let's just make sure we get that type of thinking down. So once I've thought about what receptors I might have for any of the problems, now we think about the time scale. So I first tend to think about the nervous, the milliseconds to seconds. Okay, so what's going to be happening on milliseconds to seconds? So those are really nervous effects. So what am I connected to directly through the nervous system? And you know, since fluid flux is really just all physics, that really is happening on a very fast time scale as well. Okay, and then secondly, think about the seconds to minutes time scale, and so for this it's mostly going to be thinking about hormones. So you might need to get these hormones out using the nervous system, but then once you get the hormones out, you get the hormones out on a milliseconds to seconds time scale, but their action is going to take seconds to minutes. And sometimes their action actually takes the 3rd time scale, which is hours to days. Okay, the 3rd time scale, hours to days, which is really giving some thought to what's happening at the kidney. Right, because when we're thinking about water loss or reabsorption, we can, in a milliseconds to seconds time scale, get ADH out, but then ADH needs to find its membrane receptor population and do its thing, right, which is seconds to minutes. But then when it's affecting water loss or reabsorption at the level of the kidney, we now have to just sit and wait for filtration to occur so that we can then reabsorb it. So that's why we think more of anything to do with water loss or reabsorption at the level of the kidney, that's an hours to days thing, because we really just have to wait for filtration to happen before we can get reabsorption to happen. Okay? So I think that's the kind of thinking that is really helpful when you're presented with, you know, the really big kind of problem. You know, how did the body get itself messed up, and how do you think the body is getting itself back? Okay, so that's the why we've taken all of the types of information that we've been looking at so far, so we can get ourselves to this point, to be able to start to see how the body in an integrated way is going to respond to any sort of stimulus. And so where we're going to go from here is we're going to add a system on. So we're going to go up into this pulmonary system now and think a little bit about some other regulated variables. So we've been really focusing on mean arterial pressure, but there are other regulated variables and other sensors associated with those. So we're going to go up into the respiratory system, think about how that works, keeping our eye on the regulated variables of oxygen and CO2. And then we'll be able to redo this scenario with all of the receptors associated with the regulating mean arterial pressure, and add on to it all of the receptors associated with trying to keep oxygen and CO2 constant. Because as soon as you change flow across the lung, like we've been doing over and over again, as soon as we change flow across the lung, we're going to be changing oxygen and CO2. So we're getting that messed up here as well. So we got to figure out, how do we get it messed up? Where are the sensors, and how did the body respond to get oxygen and CO2 back? Okay, then from there we're going to add on hydrogen ion, and by the time we get to that, we'll be able to revisit this with probably an answer, a solve to how the body responds to a decrease in left ventricular function, with about 4 or 5 pieces of paper in terms of trying to lay out what the answer to that problem is. Okay, and that's where we're going to go next. And so what I think we'll do is stop here for now for this lecture, and then the next lecture we will start up with the respiratory system. Okay, great, thanks.